Okay, I'm going to walk through this diagram. It's done in lecture notes, but it's a little bit easier if you actually see some presentation with a bunch of crap drawn on this diagram to help you understand the physical nature of the greenhouse effect or global warming. As it says in the introduction in the notes for this module, there's a great deal of misconceptions. Generally, if you've heard the explanation of greenhouse effect from anybody other than an atmospheric scientist, it's probably wrong. The fundamental nature that contributes to an increased surface warming due to changes in our atmosphere is actually simple to understand. It's the fact that the atmosphere, this thing, has a finite temperature. And we'll re-radiate that finite temperature as excess flux, both upwards and downwards. And the key assumption that we make in explaining this phenomenon, which does work with respect to the observed surface temperature of the Earth, is that half of the flux that's radiated upward and half of the flux is radiated downward because our atmosphere is thin. So the basic idea is the following. We got incoming short wavelength radiation from the sun, and I guess the sun is down here in this big projector spot, but nonetheless, the sun's up there. This thing called the atmosphere intercepts some of that short wavelength radiation. Some of that short wavelength radiation is lost, and so the amount that reaches the ground is some percentage times the original flux. And we encode that percentage as T sub s, which stands for the transmission at short wavelengths of the atmosphere. In our case, T sub s is about 30%, as you saw in the course material. And so there's some total flux here of optical radiation, sunlight, that hits the ground. That energy is then absorbed and hits the ocean, hits everywhere. That's absorbed by the planet, so we'll get rid of the ground here and call that planet. It's absorbed by the planet, and the planet reaches some equilibrium temperature, which we'll call T sub g, the equilibrium temperature of the planet, which I just said twice, so it's even doubly redundant, now triply. Okay. Now, that radiation that heats up the Earth has to be re-radiated to keep the Earth in thermal balance, and so the Earth re-radiates that as long wavelengths, red, infrared, long wavelength radiation, and it emits that as a black body, which you don't really need to know, but the Earth has a finite temperature of about 300 degrees Kelvin. And so it heats up at that characteristic temperature and emits radiation in the infrared. Now, if the atmosphere didn't interfere with this radiation, we wouldn't have a problem. But the atmosphere will turn out to intercept most of this radiation. It doesn't just escape directly back into space. It gets reabsorbed by the atmosphere. And so the flux that's going out of the atmosphere is the flux that's emitted by the Earth modified by the transmission of the atmosphere at long wavelengths, which for some reason the literature likes to call T sub t. It really should be T sub L for long wavelengths. And, of course, as much flux goes in as it goes out, so ultimately T sub s times F0 has to balance T sub t times Fg. That's what's in the course notes, so I won't go through that here. It's just conceptually what happens is that the atmosphere reabsorbs most of this long wavelength radiation, and so it's heated from another source. Here it's heated by incoming short radiation, and the atmosphere doesn't absorb very much of that. Then it's reheated by long wavelength radiation emitted by the Earth, and the atmosphere absorbs a great deal of that. Approximately 2/3 of the total flux emitted by the ground is absorbed by the atmosphere. So the atmosphere has two sources of heating, incoming sunlight and outgoing long wavelength radiation. And so, as a result, the atmosphere has this finite temperature, T sub atmosphere, and half of that extra temperature, so to speak, is re-radiated back to the ground, thus making the surface temperature warmer. So how do humans screw with this? Well, we screw with this in two ways. We screw with the short wavelength end by all kinds of pollutants and aerosols. Aerosols, not spelled correctly likely. So we modify T sub S by industrial processes. And most people are unaware of this, but this also would lead to global cooling if it weren't countered by the much greater effect that we do at longer wavelengths, is by changing T sub T for the atmosphere, primarily by increasing the atmospheric CO2 content and the atmospheric methane content. Those are the two principal greenhouse gases. Note, the Earth has a natural greenhouse gas called H2O, water vapor. Water vapor absorption dominates what happens in the atmosphere. The addition of these gases enhance what water vapor does, which is why this whole thing should be called the enhanced greenhouse effect. You can't talk and write big words at the same time. I'm not done. So this is a race condition between human activities that will serve to cool the Earth over human activities that serve to warm the Earth. And right now, the warming part is definitely accelerating over the cooling part. And in some sort of ironic twist, pollution laws are actually hurting in this context, because if we could put more aerosol pollution in the atmosphere, we might experience less warming. In any event, we shouldn't be screwing with the planetary thermal balance anyway, but nonetheless, we are.